And for instance, you have this particle. That would be, say, E plus. We also call it a positon, but it's a E plus. So the side A and side B are themselves spinors. Spinors. Oops. They are two components. So they are themselves spinors. So the phi here is an spinor. It's basically a wave function with four components. Okay, and now we are organized these four components with two components, and each one of them is themselves by itself a spinor. Notes. E stands for the electron. S spin half. Two. Of course, in a problem, and that's when I have probably tomorrow, when I have a Feynman diagram, and I have a Feynman diagram involving an electron, whatever, and that particular Feynman diagram will define what's the spin of the electron. Okay, and then we're going to use the solution that corresponds to the spin that we have decided it's up or down. If you are dealing in a more general situation, when you have two electrons interacting, and the electrons that are interacting may have spins up or down, then we have to consider all the possibilities. But tomorrow, just to make things simple, there's just one of them. Now, so we have. No. I don't understand why this thing does not do necessarily what I want to do. We have. Hello?
Mm-hmm.
There's some noise. There's some background noise.
Professor, the data equation is only for fermions? The data equation is only for fermions? Excuse me. The data equation is only for fermions, only that particles we had a half spin?
Yes, that's what we're doing, exactly. Yeah. The electron could be, it could be a muon, and they all are, all fundamental particles, all the electron, muon, and all the quarks, they are all fermions. Okay. Although when we have the Feynman diagram, of course, you're going to have the boson. But all these particles that you deal with, all the fundamental particles are fermions. Yeah, so that's true. They all have spin half. Because the same equation we're getting now will be the same for an electron, the same for a muon, the same for a tau. The only difference between an electron, a muon, and a tau is the mass. Okay, and the mass will show in the final solution. Okay, so when we solve for the Feynman diagram, in fact, we may ignore the fact that it's an electron or muon and just add the mass at the end. So make things a little bit easier for it. Otherwise, if we're not for the mass, I could not distinguish an electron from a muon. So let's see. The quark is a little bit different when dealing with the quark, because the quark does not have the electric charge of the quark is a fractional amount. It's not 1 or -1. You have -1/3 and 2/3. But that's all what changed with so of course the electric interaction, the electromagnetic interaction is a little bit different just because you don't have the same amount of charge as an electron, but everything else is the same. Okay? And of course the quark has a much bigger mass. Again, as I mentioned yesterday, at the end we're going to have a solution that takes the mass of the particle into consideration. But the mass of the particle is just part of the problem. Okay, a mass of the particle. A particle has an energy. So the minimum energy that the particle has is its rest mass. Okay, so if you have a particle that's not moving, the energy is its rest mass. But once you have a particle moving, the energy depends also on the momentum of the particle. So the energy will be part of the energy will be basically the rest mass of the particle plus, let's say this way, the kinetic energy. Let's make things simple. The kinetic energy. If the kinetic energy, the energy due to its speed, is much much higher than the rest mass, we can just ignore the rest mass. Okay, if the rest mass is say 2 and the kinetic energy is 20, we can just get rid of the kinetic mass. So for very high energy, the results will be pretty much the same for an electron or for a muon. Okay, and that's what we're going. Someone asked me about the problem with the spin. Yes, all these particles have spin half. All the fundamental particles have spin half, and that's what I do. And the only difference at the end will be the mass of the electron, the mass of the muon, or the tau. But depending on the energy, you can just ignore the mass, and it will be exactly the same for all the particles. Of course, a quark has a much higher mass than electron and so we must take this into consideration. And the only important thing is that the quarks do not have the electric charge in the quark is a fractional unity. So this just affects the interaction. But at the end, the equation will be the same. So we have 4 independent solutions. For P equal 0. Remember at the very beginning that we made this assumption just to make things easier. So the solutions are here. I write them in blue. So this is from yesterday. Remember, then here I have 1, 0, 0, 0. Solution 1. This is solution 2 equal to minus I MC2 is H slash T 0, 1, 0, 0. Solution 3, that's E. Now the energy is different. MC2 H slash T, then is 0, 0, 1, 0. And if you notice, these are totally independent. I M C squared 0, 0, 0, 1. Okay, if we attend, those are totally independent because they have here 4 components. And the first one, they have 1, 0, 0, 0. The second one, 0, 1, 0. So they are independent. So we cannot write this first one. We cannot write this first one as a combination of the other 3 because all the other 3 lack the first component. Okay? And again, as I mentioned yesterday, C is the speed of light, H slash that's Planck constant. And since they have strange values just because of the system of units that we invented some time ago. But what we're going to do eventually, to make things much easier for us, is just use a set of unities where the unity for speed will be C, the speed of light. So C will be equals to 1. And also the unity for H will be 1. So we just get a system unity where it's 1 and 1. So at the end, we don't have C. We have neither C nor H slash, which makes things much easier to look like. So by now, I'm leaving C and H slash there. So we have here spin up electron. positron. Spin, down, electron. And spin, down, positron. Okay? So we have the four solutions, each one of them able to represent the electron or the positron, spin up or spin down. Okay. Now, now, let's have a solution. Now, let's write in a better way. Plane wave solution. Remember that the wave function is a wave. That's why plane wave have a wave. The particles moving, we have a plane wave moving there. So let's write this way. I'm being a little bit more general now. R is the position, so it has X, Y, and Z. Okay. Eventually, we may go for something in particular. To A. Remember that the wave function must be normalized at some point, because wave function should, as it able to represent, to give you the probability of finding a particle somewhere in the universe. If you make a full integral of the wave of all space, you should have one. So you must at some point normalize the function. So this will be A E minus I E. That comes from quantum mechanics. At the very beginning, that's what I showed at the very, very beginning yesterday. Okay, so that's how a plane wave should look like. Then X. Okay, this thing here. So it's like that wave with several components, okay? This is just a notation. It looks a little bit confused. I think it's a little bit confusing, but it makes things shorter. That's a notation that originates from Einstein. I do not know how familiar with the notation you are. But rather than have a sum of many indexes, like, say, A1, B1 plus A2, in case you have A1, rather than have, say, A0, B0, plus A1 B1 plus A2 B2 plus A3 B3. Let's say we write something like this, and the I, A, B, I, and I from 0 to 3. It just makes a convention that when you have index like this one that they are repeating, you just add on the index itself. So it makes it shorter to write. So you have to understand this thing here, have a P here, a mu, and the X mu there. So there will be P0, X0, P1, X1, and so forth. Okay, it's just a simplification. It may look confusing, but since these equations at the end, they end up being so big, it's convenient to have a way to have it shorter. So if you put this, so if this would solve the direct equation, so into. So inserting this in the direct equation, and here's the direct equation. So I see we have again here, see gamma mi, and so this would be say like G, and plus 1 plus, and so on. Okay, just a way to make things easier to write. So rather than have the 4 components, have just this arrangement here. Then we have I H slash P U again equal to 0. Okay, so this equation has to be equal to 0. We have this result here. Okay, it's simple algebra, not a big deal. So in this case, U satisfies the equation so in this case P Now, relax. Okay? Be calm. Why? This is not as complicated as it looks like. Okay? Be calm. Okay? Okay. I will try to write this here in a more visible way. So, the pencil is fading again. Come on. This is equal. Remember, I gave yesterday, I showed what would be those gamma functions, okay? Those gamma matrix, they are matrix after all. So this would be, if I replace in the other equation, E over C, that's what we call P0. It's the zero component there. 1, 0, 0, minus 1. Remember, this matrix, in fact, is a 4 by 4 matrix, okay? This one, in fact, is the identity matrix. Minus P, and you have those matrix. Okay? So this is an operation that's very easy to do. So let's do it. Is EC. All you have to multiply is EC multiplied by all components of the matrix, will be EC. Then you have P. Okay? Here you have minus P sigma minus E sub C. Okay? So that's the easy expression. Then I try to keep this on the screen. Then, well, let's see. Will be E over C minus MC. Here will be minus P. Remember that P is the momentum. P. C minus MC. A and the U, B, the two components. Okay. This is equal to C minus MC. A. Here you have P. Okay. That's just do what the usual matrix multiplications. First line, and you have just one column. The second line and one column. That's what you get here. C plus MC. Okay, this is equals 0. Then wait, this is not working. So if you solve this thing here, it's not a big deal. If you recall well, mc squared is basically the rest energy of a particle, the energy of a particle due to its mass. So as I told you before, if the energy itself is much bigger than the rest mass of the particle, you can just ignore E minus mc squared will be pretty much equal to E. And here is E plus mc squared. But it's the same. If mc is much smaller than the energy, you can ignore it anyway. Okay? Now, the matrix is always good to recall. We have this one here, that is 0, 0, 1, 1, 0, okay? And is 0 minus I 0, and one, 0, 0 minus 1. They are called they are the Pauli metrics. Pauli was another physicist who also worked with this kind of thing. So, if you solve all these things, it's not that complicated. Then we have the P. Sigma will be Px, the component, momentum component x, times this matrix here. Okay? This component will be 0, 1, 1, 0, plus Py, and be 0 minus I 0, 0, plus V 1, 0, 0 minus 1. So the x component of the momentum multiplied by the x component, let me talk this way from the Pauli matrix, the y component of P goes multiplied by the y component and so on, because that's what we have here, okay? It's pretty much like a scalar product, okay? You see this as components. You operate the same way as you operate with the vector, if you had to make a scalar product with the vector. No? So, my goodness. So if we make all these calculations, that's not much, but I'm not going to the trouble of doing it. Okay, we have UA P2 C2 E square minus M2 C4 I'm sorry, but my Apple Pencil is not working. Remind, there's a very important expression to know. That's the E squared minus M2C4 equal to P2 C2. This is the energy momentum relation. That's the same that we use at the beginning to get to the Dirac equation. Okay. And then, so we have E, because remember this is E squared. So when you get the energy itself, you get a positive value and a negative value. So E equal to plus P2C and the other one is E equal to minus this one at the top. This is for a particle. And this for the anti-particle. Okay, particle and anti-particle. So then, putting all this together, okay. So let's put all this together in one simple form. Then what you have this U A that will be simple 1, 0. B equal C E plus MC squared zero, and this is equal to C, the speed of light, and C squared. Here have PZ, and here have PX plus IPY. In our example, we're really going to have for a Feynman diagram. We make things very simple. So we are going to have the particles only moving in the z direction. So there will be no x and y components. So the second row here will be 0. There will be only, of course, it's totally arbitrary what you call z, x, and y. But in principle, the direction of the particle we call z. So in our example, we're going to have a particle just moving in the z direction. So px and py will be 0. The equation could be simple. And we're also going to have the energy so high that the term that mc squared would not be relevant. So we're going to have only c, e, and c be equal to 1. So that's, I think, very simple. This is for UA. Another situation, let me mark it here, it is as A. The other situation, CB. Then we're going to have UA equal to, the other case, 0, 1. No, doesn't work. C plus MC2, the same thing. And here we have 0, 1. So this is equal to C E plus MC squared. And it will be Px minus I Py minus Pz. Okay? The third case, C. Now you have UB 1, 0. See? Now be E minus MC squared P sigma. And again, 1, 0. C E minus MC squared P Z, the Z component of the momentum, Px plus I Py. And finally, zero, 1, A, E, my MC squared, P sigma, 0, 1, that'll be C, E minus MC squared, Px minus I Py minus Pz. Okay, of course nobody has to memorize all this thing, okay? So we have here four independent solutions. Okay? And A and B for E equal to M2C4 plus P2, C2, and C and D for E equal to minus M2C4 plus P2, C2. So those are for the antiparticle. Okay? Now, you're almost done. So, as I mentioned before, you must normalize the thing. Huh? Because all these, when you describe the particle, you have the integral of the position has to be 1. Now, I'm going to use a symbol. Let's say I have a matrix A. Let's say I have a matrix that to say is A, B, C, and D, the matrix. Then I have defined what we call a dagger. That's just C. Yeah. And B. So this is the conjugate transpose. What you do is that you just exchange this is the row. Huh? You have the row. And here you have columns. To transpose the matrix is just replacing the rows by columns. So A, B, C, D, you be here have A, B, C, D. Now you have A, B, C, D. And then you get the conjugate of the number. Of course, if the number is a real number, it's the same. The conjugate number for a real number, imply the A conjugate is equal to the number. But a complex number say A plus B Y is equal to A minus BY. Okay? That's the conjugate. So for the real number is the same. For a complex number, it's different. Now, let me get some of my paper here. It's in a bad position. So where am I? And then, if Z is equal to A plus BI, then where is the modulus, né? Basically, A2 plus B2. So the square of the modulus of a complex number is just the square of the real part plus the square of the imaginary part. So it's easy to demonstrate this, and then we can see that sorry. So the square of the modulus of a complex number is just the number itself times its conjugate. complex conjugate. Okay, so the solution U1, I call it N. N is the factor that allows for the normalization. It will be 1, 0, C, B, Z. I'm putting together all those parts, part A and part B. A plus MC square C. I know that all this is scary, but we're not going to use all these complicated things when we really calculate the Feynman diagram. So we're going to just call it U. And only at some point we're going to write U as this long and complex expression. E plus MC square. Okay. U N, let's do the normalization. V0, 1. Now we have C Px minus I Py E plus MC square. And here you have C minus BC again, E plus MC squared. It gets much simpler if the particles just go in this direction, as we are going to do. And then you have U3. That's all as again N. C PZ E minus MC squared C Px plus I Py E minus MC squared, 1 and 0. And finally, U3, that's equal to N again. C Px my I Py E minus M C squared. C minus P Z. So C zero 1. Now E remain E equal to plus or minus, depending on the situation. Let us, for this 2 here, yeah? For the first 2 here, E is equal to plus minus M2C4 plus P2C2, yeah? And will be equal to E plus MC squared over C. Okay, so the energy is positive sign for the first 2, corresponds to the particle, okay? And to the minus signal to the 3, this one should be 4, no? And makes the normalization of this whole process. Okay. However, and just to make things a little bit more interesting, that we can use a similar approach for the antiparticle rather than writing the energy. Here we're having the energy for the antiparticle like negative. So we can consider the energy positive and just change the signal. Yeah? But anyway, just to make things faster for us. Huh? So we have basically U1 and U2. Huh? 2 states. Two states. 2 states or 2 spins for 2 spins. Of the electron. And writing electron, it could be a moon of energy E and momentum B. Okay, it is satisfied. Okay. So those are the 4 equations that we and 4 waves that represent for all purpose the electron or the positron or muon or whatever. And that's what I'm going to use, but not with this long expression, to calculate the Feynman diagram. So we still have time today, so I can start. I'm going to finish today because it's too much for us to see. But let's now forget about this, all this complication, okay? And see what you do for Feynman diagram. Let's now see finally the Feynman rules. For QCD. This is quantum electrodynamics. Okay? So how to calculate the amplitude the same that we did for the toy model, if you remember well. Let me see my expressions here. Okay? So we do exactly the same thing. We have here a region or some things happen. And we have particles in, in, okay. Let's say here, for instance, we have, for instance, P1 and has a spin 1. You have, say, P3 and the spin 3. Wow. No? So the rules are pretty much the same, very similar to what you have for the toy model. So one, mark. Have again to goodness. Let's see what's okay. Again. Let's see if it works, because it's bothering a lot. Get your particles. Get it into and out. And mark the quadrimomentum as before. Momentum. P1, P2, okay, how many? Pn, and the spins. S1, S2, Sn. Because that's the you define which of those functions you want to use. If you have a spin up or a spin down, and if you have a particle, antiparticle. Now we're going to have internal arrows. And external particles. No, sorry, particles and antiparticle. And here, so the flow. So the external ones entering or leaving the system, they are either particles or antiparticles. It could be electron, muon, neutrinos, or whatever. But remember talking about QUD, so QUD, neutrinos not to be involved here because neutrinos do not interact electromagnetically. So now the second step depends on what we're going to do. Now, for each external external line. Remember, external line is a particle, right? External line, you're going to have vectors. What vectors? Okay, if you have electrons, or muon. We have two situations. You may have electron go into, or you may have them living. So the electron may be go into one of the knots when they have some interaction, or it may living. In this case here, you use that function u. If it's living, it will be u bar. U bar will be, I will explain tomorrow what's the u bar. It's going to, you remember they have u as a column. Okay, so column vector here, pretty much like a column vector. Okay, it's a column. The u bar will be the transpose of this column, but inverting some of the components. Okay, I will show this when you have to do it. Okay. If you have a positron or muon, mean an antiparticle, no? So we're not going to use the U particles that we used to do with the particles. Remember that these particles here, when you have this thing that we call U, here we have a negative energy. So the approach that is done is not have a negative energy. So energy will be all positive, but they're going to add a minus signal to all the other components. What's pretty much the same thing, okay? But in this case, the energy, rather than have a go with a negative energy, you have a positive energy and change the signal of the other things. We call this V, and we see tomorrow all this. But this is going to be V, well, and V. Okay? Now, the third step more, we go one by one and make a calculation. Now, the third step, well, they have the vertices. I'll have the vertices. Right? So each vertex will have a factor that will be I, G. Remember that the toy model, each vector had a factor that was I, G. G was the coupling of the interaction, okay? G, E. E from the electromagnetic interaction, gamma. Case 4P. For each vertex, you have to include this factor here, I, G, E, gamma, mu. Okay? Now I have to call attention for an important fact that I said before, attention. Quarks have right? Mary Arch. So the coupling will be not as intense as with for an electron. Now we have the propagators. Remember that connects to the two vertices. For each propagator, we're going to have electron or positron, doesn't matter. I, Q square minus M2 C2. And the M, of course, is the mass of the electron. That's the propagator itself. But if the propagator connected to vertex is just happens to be a photon, this is going just to be minus I J mini. We're going to see what G mini tomorrow. Q2. Okay. Now, the same thing that happened for the toy model, you must conserve energy and momentum. Energy and momentum must be conserved. So, then you have your 5. Conservation of energy and momentum. The same as before. Okay, so it will be exactly the same as 2 pi 4 delta function k1 plus k2 plus k3 plus, okay? Again, k momentum going into the vertex. And again, as the toy model would be positive, that's positive, it will be positive into. Why this thing does not work? It's a so expensive device. Into a negative. It's exiting. So if the exiting, the vertex k is negative. It's the same thing as we did for the toy model. Then 6 integrate. Integrate over the internal moments internal so the same as it applied moment for each to be.
¿Me escucha?
Ahora sí, ahora sí.
Seven. Cancel. The delta. Remember the delta functions, they're just to assure conservation of energy. The result will have a factor as 2 pi to the 4th the momentum okay, that assures again. Remember the momentum and energy must be preserved at each vertex and for the whole thing. So, energy and momentum. Okay? So, again, we cancel this term. The same as we did for the toy. And then we have the expression for the be exactly pretty much the same thing as we. So minus IM is the result of all this thing. As was for the toy story. Okay, or the toy game. So what we're going to do today is apply this simple case. And then once you apply, to make a calculation, you get a real number. I could start this today, but I think I did already a lot today. I'd rather be more efficient if you do tomorrow, because tomorrow people will have forgotten everything about this complicated direct equation, and you can just concentrate on the Feynman diagram and finally have one result from the Feynman diagram. So although we still have some time, I think that's enough for today. Okay, we saw the basics of how to have an equation for the Feynman diagram. All I have to do now is to apply this to a simple case and make a calculation. And you'll see that it will not be as complicated as it may sound. Okay, at the end, we're going to just use the big problem was just to write the functions, the use for the particles, and then see how it happens today. We're going to do it for electron and muon and get a result. Okay, I will stop right now because I think it was a lot today. Lots of calculation and going ahead would not be productive. And we'll have enough time tomorrow to finish. Okay, and if you have questions, I'm sure you have questions. I doubt that everybody understood everything. In fact, it's more likely that people understood almost nothing. Just send the questions, okay? And of course, if you go to the bibliography that I sent, and I believe Professor Castro had distributed, you can see this with more details, and they go slowly and slowly through all the pages. Hello? Hello?
Yes, hello.
Okay, so I'm stopping for today. So please send your message with the questions, okay?
All right, thank you.
Las diferentes preguntas, por favor, por email para él. Muchísimas gracias.